So in today's video, I'm going to talk about the simple pendulum. So you may have seen that objects that are hanging from some point usually create some kind of a to and fro, back and forth oscillations. Now, if you have an object that can be approximated by a point mass, like a ball that is hanging from a string, that kind of a setup is known as a simple pendulum. It's called a simple pendulum because that is the simplistic or simplest construction possible. Now the question is the nature of the motion simple enough? Well, we will see. Okay, so what can you expect from today's video? First of all, I'm going to look at the forces that are involved and I'm going to obtain the equation of motion of the simple pendulum. I'm going to do that by applying the Newton's second law in polar coordinates. That's the first thing. Second, I'm going to look at the torque involved and the nature of the rotation, and from there I'm going to obtain the equation of motion, the same equation of motion. And third, I'm going to obtain the same equation of motion by looking at the energies, by looking at the Lagrangian. Now you may say, why am I obtaining the same equation of motion of the pendulum from three different approaches? Well, why not? I mean, if you can obtain the same equation of motion for the system from three different approaches, I mean, that is quite interesting, isn't it? So let us do that. And once you do obtain the equation of motion, which is a second order differential equation that needs to be solved. But the question is the equation even solvable in the first place? For that, we will have to look at some approximations, especially the small angle approximation. So once we do the small angle approximation, now that becomes a differential equation that can be analytically solved, which we are going to do. And then we are going to look at the nature of the solution. What is the displacement? What is the velocity? What is the momentum? What is the energy, etc. I'm also going to do one more thing. I'm also going to try to solve the equation of motion without doing the small angle approximation, which can be done not analytically, but using some kind of a computational software that is capable of solving differential equations numerically. For that, I'm using Scilab. And once we do that, we will compare the results for small angle approximations and the results without considering the small angle approximations. And we will see how that is different from each other. Then we will also look at the phase space trajectory. We will look at how the momentum varies for both small angles as well as for larger angles. We will also look at how the kinetic energy and the potential energy varies for small angles as well as larger angles. So it's going to be a little bit of an elaborate video. If there are portions that you want to skip through because you're already familiar with it, you can do that. I'll put a timestamps for the various topics in the description. So let us begin. So here we have a very simple construction of this pendulum where there is some kind of a mass that can be approximated by a point mass that is attached to some kind of a massless, inextensible string that is hooked at some kind of a pivot to a ceiling or the wall. And the nature of the motion is restricted to a plane. In that kind of a situation, we can obtain the equation of motion by looking at the forces involved. Now, what is the most obvious force in this kind of a situation? Well, the most obvious force is the force of gravity, which is mg acting downwards. There is a force which is the force of tension. The tension is existing there because the massless string is inextensible, and it is because of this tension that the pendulum's motion is restricted to the arc of a circle. Now, if I want to analyze the nature of its motion, I will have to look at the forces that are resulting in this kind of a motion on the arc of a circle. For that, I can look at the components of the forces. So for example, if mg is directed straight downwards and I look at any random point where the pendulum is present at any random point such that the angular displacement from the vertical axis is theta, then I can divide the force mg into various components. One, I can look at the component along the radial direction. Now, if you look at the geometric construction here, this angle is the same as the angle theta. All right, so the component along the radial direction is simply going to be equal to mg cos theta, right? And the component of the force along the tangential direction is going to be simply equal to mg sine theta. All right. Now, it is clear from the diagram that the radial force is not contributing towards the motion because the radial distance is a constant of time. It is only the tangential force component that is responsible for the to and fro motion along the arc of a circle. So let's first obtain the equation of motion from the Newtonian perspective by applying the Newton's second law in polar coordinates. The Newton's second law says that the force acting on any kind of a point mass object leads to some kind of an acceleration A. However, because the nature of the motion is along the arc of a circle, we can apply the polar coordinates. We can write the Newton's second law in polar coordinates. So if you write the Newton's second law in polar coordinates, this simply becomes the force components along the radial direction, the force components along the transverse or the tangential direction, is equal to m, the acceleration component along the radial direction, plus m, the acceleration component along the transverse or the tangential direction. Now, if you know how to transform the acceleration terms from xyz to polar coordinates, then you would probably know that the first term here simply represents r double dot minus r theta dot square r cap, and the second term is m r theta double dot plus 2r dot theta cap. Don't be scared of the dots here. The dots simply represent time derivative. So a singular dot represents single time derivative. The double dots represent second order time derivative. Now, if you look at the forces Fr, which is basically equal to this particular term, and if you look at F theta, which is basically equal to this particular term. Now you must understand from the diagram itself that Fr is not creating any kind of a motion because the radial distance of the pendulum is not changing. L is a constant of time. So the only thing that we are interested here is the relationship between F theta is equal to m r theta double dot plus 2r dot theta dot. Again, theta represents the angular displacement, r represents the radial displacement. The radial displacement is the distance from, let's suppose, the point O to the pendulum's point mass, and theta is the angular displacement with respect to the vertical axis. Now, in the construction of the pendulum, the r dot is equal to 0. Why? R dot simply represents time rate of change of the radial displacement. The radius of a pendulum remains constant with time. That is the construction of a pendulum. So this is equal to 0, and r here is simply equal to L, is a constant of time, right? This is the first thing. Second, what is F theta? F theta is the force along the transverse direction, which is nothing but mg sine theta. Now I have to write the minus sign here because the force is acting in a direction opposite to the increase in angular displacement. So the direction in which the angular displacement is increasing is in this particular manner, but the force is acting in the opposite direction. So the force is acting in a direction of the decrease of the angular displacement. Therefore, I have written the negative sign here. So minus mg sine theta is equal to mr theta double dot, which leads to the equation minus g sine theta is equal to r theta double dot. If I substitute the values here, this simply becomes minus g sine theta. R is nothing but the length of the pendulum, and theta double dot is d2 theta upon dt2. This becomes a very simple differential equation. If I write it properly, this is d2 theta upon dt2 plus g upon L sine theta is equal to 0. This is quite simply put the equation of motion of the simple pendulum that you can obtain just by looking at the forces that are involved, more specifically the force acting in the transverse direction written in terms of polar coordinates. Now I can obtain the same equation of motion but using a little bit of a different approach. Let's try that also. Now, of course, the nature of the motion is some form of rotation here, right? So if you apply the Newton's second law in terms of rotation, then you can write that whatever the torque is that is creating this motion is the result of I alpha, where I is the moment of inertia and alpha is the angular acceleration. This is quite simply put the nature of the Newton's second law in terms of rotation. So here the moment of inertia I is what? If you look at the pendulum, of course the string is massless by our assumption, and the mass is a point mass at a distance of L. So the moment of inertia is quite simply put ml square, and the angular acceleration is simply defined as the second order derivative of the angular displacement, which is d2 theta upon dt2. Now what is the torque involved in this kind of a setup? The torque is simply nothing but r cross f. Okay, so if you look at the torque is, if I write it only the magnitude of the torque, that is nothing but r cross f. Now what is f here? As I already said, the force is the force of gravity, but it can be divided into two components, one along the radial direction, the other along the transverse direction. The component along the radial direction is not causing any change in the radial displacement. It is only the component along the transverse direction that is leading to the change in angular displacement. Therefore, I have to write here r is nothing but the distance from the origin O, which is nothing but L. Okay, and since L and mg sine theta are perpendicular to each other, therefore the cross product will simply involve the length of r, that is L, cross product sine 90 comes out to be 0, and force is mg sine theta, and this is a minus sign here because it is acting in the direction opposite to increasing theta. So this simply becomes an equation where minus mgl sine theta is equal to moment of inertia is ml square and alpha is d2 theta upon dt2. Here of course the masses get cancelled out, the L of course also gets cancelled out, and you are left with minus g upon L sine theta is equal to d2 theta upon dt2, which can be written in the form of an equation d2 theta upon dt2 plus g upon L sine theta. This is exactly the same equation of motion that we just now obtained by taking a look at the forces. So even by using the concept of torque and moment of inertia, we can obtain the same equation of motion. Now let us again obtain the same equation of motion, but using a little bit of a different approach. Some of you may have heard of it, some of you may not have, and this is known as the Lagrangian approach, which is the approach that is used in classical mechanics. So in the Lagrangian approach, instead of dealing with forces, we deal with energy, specifically the kinetic and the potential energy. Now, if you are completely not familiar with the Lagrangian approach, you can skip through to the next section where I'm analyzing the equation of motion. Okay, so in the Lagrangian approach, we basically look at the kinetic and the potential energy of the system. So the kinetic energy of the system, or which is written as either Ke or T, is simply equal to half mv square. Now, as I already told you that the nature of the motion is restricted to the arc of a circle, it's always better to write the physical quantities in terms of a coordinate system which makes sense in that sort of a motion. So the coordinate system that makes sense here is the polar coordinates. So in polar coordinates, the velocity is written as simply v square is vr square plus v theta square, where vr is the velocity along the radial direction and v theta is the velocity component along the transverse direction. Now some of you may already know, if you are familiar with polar coordinates, that vr is nothing but r dot and v theta is nothing but r theta dot. Quite simple. So if I apply this here, the form of the kinetic energy simply becomes half m r dot square plus r theta dot square. That's it. This is the kinetic energy. What about the potential energy? Well, to find out the potential energy, we will require a reference with respect to, let's suppose, the zero potential. Now I can choose the reference to be the ceiling or the point of the pivot, or I can choose the reference to be also the lowest point of the pendulum. So if I choose the lowest point as the reference for the pendulum, in that kind of a situation, what is the height? Let's suppose the height of the pendulum is given by h. Now I can calculate h in terms of the length of the pendulum, because as you see here, the projection of the length of the pendulum along the vertical axis is simply nothing but L cos theta. So if you calculate the height is nothing but L minus L cos theta, as it is obvious from the construction here. So the height is simply L1 minus cos theta. Therefore, the potential energy is mgh, which is nothing but mgl1 minus cos theta. So if you are not familiar with the Lagrangian is simply defined as T minus V. So this is equal to half m r dot square plus half m r theta dot square. Sorry, this is supposed to be r square, okay? R square theta dot square minus mgl 1 minus cos theta. Now what do I do with the Lagrangian? What we do is we plug it into what is known as the Euler-Lagrange equation. When we plug the Lagrangian into the Euler-Lagrange equation, that is when we obtain what is known as the equation of motion. So the Euler-Lagrange equation is written in this manner: d upon dt of del L upon del Q dot minus del L upon del Q is equal to 0, where Q is supposed to be the generalized coordinate. So generalized coordinate is just the coordinate with respect to which you're analyzing the motion. Here we are trying to analyze the motion with respect to the angular displacement. So I'll assume that Q here simply represents theta. So the Euler-Lagrange equation is simply d by dt del L upon del theta dot minus del L upon del theta is equal to 0. So here, as you can see, if you look at the Lagrangian, I can find out the various derivatives of the Lagrangian with respect to the various quantities. So here, del L upon del theta is simply nothing but minus mgl sine theta. Del L upon del theta dot is equal to m r square theta dot, and therefore d upon dt of del L upon del theta dot is equal to m r square theta double dot. So if I plug all of these equations back into the Lagrange equation, I simply therefore obtain an equation of the form m r square theta double dot minus mgl sine theta is equal to 0. The m is common, I can take it out. It simply is r square theta double dot plus gl sine theta. Now what is r? R, I have already mentioned, is nothing but the radial distance of the point mass from the origin O here, which is L, okay? So therefore I substitute here r square by L square, and if I divide the equation by L square, I simply get d2 theta upon dt2 plus g upon L sine theta is equal to 0. This is the equation of motion that we have obtained using the Lagrangian approach, which is exactly the same as the equation we have obtained using the concept of torque, as well as the equation we have obtained from the concept of forces and polar coordinates. So it is the same equation of motion. If anybody asks you this kind of a problem in an examination, you don't have to do all three approaches. You just choose any one of them. It doesn't matter. The reason I am doing it, because it's kind of interesting to see that the same equation of motion can be obtained from so many different ways. So this is kind of interesting in a manner. So this is the equation of motion. And the next challenge is now, can we solve the equation of motion? If I am able to solve this equation of motion, then the solution will give me something like theta t. It will give me the angular displacement with respect to time. But the question is, can I in fact solve this equation of motion? Well, you see, analytically, that means using the ideas of mathematics in solving differential equations, this kind of an equation is difficult to solve analytically. It can be solved in two situations. It can be solved either by some kind of a computational software, or we can make some kind of an approximation which will transform this equation to something that can be analytically solved. So I'm going to do both of that. So first, let us look into the small angle approximations. So in this small angle approximation, what we consider is that we assume that the pendulum is oscillating in such a manner that the angular displacement is quite small. Okay, the angular displacement of the point mass from the vertical axis is quite small. If the angular displacement is quite small, in that kind of a situation, we can make a particular approximation that sine theta, this particular function of theta, is approximately equal to theta itself. We can take a look at their graphs. So here you see I have simulated the sine theta graph as well as the theta graph. Now, of course, the theta graph with respect to theta itself is a straight line, while sine theta with respect to theta is the obvious function that you already know of. Now, if I consider a very small region where, let's suppose this is for corresponding to 90 degrees, right? So if I go up to from 0 to 45 degrees, so if I go from 0 to 45 degrees, as you can see, the red line represents theta, the blue line represents sine theta. So clearly, as theta is decreasing, sine theta and theta kind of coincide. If I even go to smaller angles, let's suppose from here to here, now both of them are kind of indistinguishable. So the sine theta varies in such a manner that for very, very small angles, like let's suppose 5 degrees, 10 degrees, the function is almost equal to the variable theta itself. So coming back to our expression, as I showed, sine theta is near about equal to theta if angular displacement is very small. In that kind of a situation, how does the equation of motion look like? The equation of motion simply looks like this: d2 theta upon dt2 plus g upon L theta is equal to 0. Now, this is an equation of motion that can be analytically solved, and we can obtain that solution and we can study that solution. So let us do that. Now, there is a standard solution for differential equations of this form, and if you are already familiar with that kind of a solution, you can skip forward to the timestamp that I've provided where we will analyze the results. But if you're not familiar how to solve this kind of a differential equation, so you can stick with me. Here G and L are a constant, and we're going to assume that G upon L is something called omega square. Now what omega is, I'm going to come to that in a moment. But the moment I do this substitution, the equation becomes d2 theta upon dt2 plus omega square theta is equal to 0. What is the solution of this kind of a differential equation where omega here is a constant? Well, to do that, equations of this form, their solutions theta are written in terms of the complementary function and the particular integral. Now, of course, this will require a little bit of an idea of how to solve differential equations, and I'm assuming that you have some kind of a idea of how to approach differential equations. So differential equations of this form can be solved by looking at their what is known as auxiliary equation. D square plus omega square is equal to 0, where D simply is a representation of the second order derivative that we have here. If I solve this, this simply becomes D square is equal to minus omega square, or D is equal to plus minus I omega. So this is a complex root 0 plus I omega and 0 minus I omega. So for complex solutions, the complementary function can be written in terms of some kind of a constant C1 e to the power 0 plus I omega t plus some kind of a constant C2 e to the power 0 minus I omega t, which is quite simply put C1 e to the power I omega t plus C2 e to the power minus I omega t. This is the most general expression for the complementary function where the roots of the auxiliary equation are complex. Since the right hand side of the differential equation is 0, the particular integral in this case also comes out to be 0. Therefore, the solution of the differential equation here, that is theta, which is a sum of complementary function plus particular integral, is nothing but C1 e to the power I omega t plus C2 e to the power minus I omega t. I can simplify this by writing the expressions in terms of sines and cosines. Now you may already know that the exponential e to the power I theta can simply be written as cos theta plus I sine theta. So if I write down my solution in these terms, this becomes C1 cos omega t plus I sine omega t plus C2 cos omega t minus I sine omega t. So this simply becomes C1 plus C2 cos omega t plus I C1 minus C2 sine omega t. So as you can see here, C1 plus C2 is nothing but some kind of a real constant, while I C1 minus C2 is nothing but some kind of a complex constant, which I can denote by, let's suppose, A cos omega t plus B sine omega t. So A here is a constant, so is B. So this is the expression for the general solution of theta. So the solution for the equation of motion of the simple pendulum under small angle approximations is simply given by theta is equal to A cos omega t plus B sine omega t. However, this is a very general form of a solution. We want to obtain a particular solution for a particular given initial conditions. So basically what I'm going to consider is that, let's suppose the pendulum is stretched from its equilibrium to a particular initial condition, that I stretch it to a particular angular displacement theta naught and I just leave it without giving it any initial velocity. Under that kind of an initial condition, we can find out the values of the constants A and B. That would give us a little bit of a better expression to study. So let's do that. Let's apply the initial conditions. So according to the initial conditions, I'm saying that theta at time t is equal to 0 when we displace the pendulum from its equilibrium position is some kind of a value, let's suppose theta naught, some small angle theta naught, maybe 5 degrees, maybe 10 degrees, something like that. And theta naught, which is the velocity that we impart at time t is equal to 0, is 0. That means we don't give it a push, we just stretch it from its equilibrium and leave it there. Now what should this give us? So theta at time t is equal to 0 is nothing but A cos 0 plus B sine 0. Now you may already know that sine 0 is nothing but 0, while cos 0 is equal to 1. And theta at time t is equal to 0 is theta naught. So this is equal to A. So theta naught is nothing but A. All right. While on the other hand, and if you find out the time derivative of theta, the time derivative of theta can be obtained from this expression. The time derivative of theta is nothing but A omega minus sine omega t plus B omega cos omega t. Now I have already mentioned that we do not give it any kind of an initial push, but rather separate it from its equilibrium and leave it there. That means we don't give it an initial velocity. So the initial velocity at time t is equal to 0, at time t is equal to 0 is 0. So this is equal to minus A omega sine 0 plus B omega cos 0. Again, sine 0 is 0 while cos 0 is equal to 1. That simply gives us that B is equal to 0. So by giving the initial conditions that we displace the pendulum from its equilibrium by a very small angle and then leave it there, by doing that I have obtained the values of the constants A and B. If I substitute it here, I finally get the solution of the pendulum for our situation of initial conditions, which is theta t is equal to theta naught cos omega t. Right? I put up the values of A and I get theta t is equal to theta naught cos omega t. So I simply get a cosine function, or I get some kind of a sinusoidal motion, because what is cos omega t? Cos omega t is nothing but sine pi by 2 plus omega t. So what I end up getting is a simple harmonic motion. I end up getting a sinusoidal trajectory. We can look at it graphically. Okay, so here I am simulating the solution for a pendulum that has been initially displaced from its equilibrium by 15 degrees. As you can see, the pendulum is displaced by 15 degrees. Here the axes are written in terms of radians, okay, and the pendulum then comes towards the equilibrium, goes to the other side, reaches the extreme, again comes towards the equilibrium, goes to the other side, reaches the extreme, and this kind of a to and fro motion is happening. What is interesting is that this kind of a to and fro motion is nothing but a simple sinusoidal wave. It is a simple harmonic oscillation. So when we solved the equation of motion for small angle approximations, we obtained a result which is simply sinusoidal oscillations, which is known as simple harmonic oscillations. So the pendulum basically behaves as a harmonic oscillator for small angles, right? So the pendulum is behaving as a harmonic oscillator. It is executing some kind of an SHM for smaller angles. Now, what is the frequency and various other quantities associated with this kind of a harmonic oscillator? Well, we can obtain it from the nature of the solution here. So solution is nothing but theta t is equal to theta naught cos omega t. The theta naught simply refers to the amplitude, right? What is the amplitude here? That simply gives us an idea about the theta naught, which is the initial displacement of the pendulum, right? What about omega? What does the omega tell us? Omega tells us, I told you, right? What is the omega? The omega, we initially assumed that omega is equal to root over g upon L. You remember? We initially assumed that when we were constructing the differential equation that omega is nothing but root over g upon L here. Now, as you can see from the solution, the omega is nothing but the angular frequency of this kind of a simple harmonic motion. By looking at the nature of the motion, which is the SHM, you can see that the omega is nothing but the angular frequency. And if you know the angular frequency, you can obtain the frequency, you can obtain the time period. So the angular frequency is simply equal to root over g upon L. So you can obtain the time period of the pendulum also. So if a pendulum is displaced from its equilibrium by a very small angle, what is the time taken for one complete oscillation? That is the time period of the pendulum, which is simply given by t is equal to 2 pi upon omega, which is equal to 2 pi upon root over L by g. Now it is very, very interesting to note that when we look at a simple pendulum which is displaced from a very displaced by a very small angle from its vertical axis, the time period only depends upon the length of the pendulum, the acceleration due to gravity. Now what is interesting to note here is that the time period is not dependent on the mass, it is not dependent on the angular displacement also. It is only dependent on the length of the pendulum and the acceleration due to gravity. So you may have a heavy object or a light object at the same distance from the pivot, and then they will create the same kinds of time periods, even for smaller angles as well as for a little bit larger angles, let's suppose 15 degrees or 20 degrees. So the time period is independent of the mass of the pendulum as well as the initial angular displacement. Now remember that we are only considering those cases where the initial angular displacement is small, because only in those situations I have proved to you that the nature of the motion is a simple harmonic motion. Okay, so by looking at the equation of motion for the simple pendulum that we have obtained, and by making an approximation that for small angles we have obtained the solution to be that of a simple harmonic motion. And from here we can obtain various other quantities also. So for example, we can also obtain what is the nature of velocity. How does the velocity of the simple pendulum change with time? As the pendulum is oscillating back and forth in some kind of a simple harmonic fashion, how does the velocity component change? Well, that can simply be obtained by looking at theta dot. So what is theta dot? It's a time derivative of theta. So this is d by dt of theta dot cos omega t. As you can see, this gives us quite simply minus omega theta naught sine omega t. So this is also a kind of a sinusoidal function. So here I have created a program to plot the SHM angular displacement as well as the velocity. The blue line represents the angular displacement and the red line represents the velocity. Now, of course, the amplitude of the velocity and the amplitude of the angular displacement is not necessarily same. Therefore, one is a little bit larger than the compared to the other, but both of them are simple harmonic in nature, although they are not necessarily in phase. The blue line decreases initially because angular displacement is decreasing, but the red line increases, although in the negative direction. So therefore, the magnitude is increasing. Now, before we analyze other quantities like momentum, I want to do something interesting. Let's go back. Okay, let us go back to the equation of motion that we had obtained. Now, the solution that we obtained was for a very specific case of small angle approximations, right? Now, what if we do not make the small angle approximation? What if we want to find out the nature of its motion if the pendulum was displaced to, let's suppose, a large angle? If the pendulum was displaced to a large angle, what would be the nature of motion there? For that, we will have to solve this equation, right? However, as I just now told you, this is an equation that is difficult to solve analytically, but it can be solved by some kind of a computational software that is capable of solving differential equations numerically. You see, usually we solve differential equations analytically by looking at the logic of mathematics and the flow of it. But there are certain kinds of differential equations which cannot be solved analytically, but they can be solved numerically by various numerical methods. So if you know some kind of a computational software, you can use that to solve this kind of a differential equation. I have used Scilab. So maybe you know Scilab, maybe you do not know Scilab. If you do not know Scilab, maybe you know something else like MATLAB or Mathematica or some other programming language, Python, in which you can create some kind of a program to numerically solve a second order differential equation. Then you can analyze this equation. Now, I'm not going to go into the details of the program that I have created. I'm just going to show you the nature of the solution that I've obtained from the simulation of numerically solving a second order differential equation of this particular form. So let's go to that particular program. Okay, so here I have created a program in Scilab to find out the nature of the solution of a second order differential equation. No need to go into the details of the program. If you are familiar with Scilab, you can copy it from here and try to create the program yourself. Otherwise, just look at the results, because it is the results that we are interested in. If we solve that second order differential equation using some kind of a computational software, then what I can do is I can look at the solutions for various angles. So here in this particular line, so I have taken mass to be 1 kg, length of the string to be 0.5 meters, and time period from 0 to 2 pi, and acceleration due to gravity is 9.82 meter per second. And here I'm taking for 4 different situations. If the pendulum is displaced by 10 degrees, what is the nature of its solution? If the pendulum is displaced by 15, 30 and 45 degrees, what is the nature of its solution? Let us take a look. So here it is. So here you can see the 4 different solutions for theta is equal to 10, 15, 30 and 45 degrees respectively. So as you can see here in the 4 graphs, the first graph represents the motion for theta is equal to 10 degrees. Second graph represents the motion for theta is equal to 15 degrees. The third represents motion for theta is equal to 30 degrees. And the fourth one represents motion for theta is equal to 45. Now there are 2 plots in every single graph. One is a red line, the other is a blue line. Can you see that? One is a red line, the other is a blue line. The red line represents some kind of a sine wave, some kind of a sinusoidal motion. Simple harmonic motion. The blue line is the solution corresponding to the differential equation where the sine theta term was present. Remember, the original differential equation contained the term sine theta and not theta. So the blue line is the actual motion of the pendulum. The red line is the solution for simple harmonic motion. Now let us look at the first graph. The first graph is for displacement 10. Here, if I zoom in, you can see that the blue line and the red line are very near to each other. They are almost merging together. So what does this mean? It simply means that the blue line, which represents the motion of the pendulum, the blue line represents the motion of the pendulum, and the red line, which is simply an SHM, are both merging together. That means the pendulum creates a simple harmonic motion. Now if I go to the second graph for initial displacement is equal to 15 degrees, again you can see that the blue and the red line are kind of merging, but there is a certain amount of distance between both these two solutions. So even though the pendulum is creating SHM, but you can see that the blue line and the red line is slightly separate from one another. Yes. Now if I go to initial displacement 30 degrees, you can clearly see here that over time the blue line and the red line are sort of separating from each other. That means the red line, which represents this simple harmonic motion, and the blue line, which represents solution of the pendulum, are not exactly in phase as you go forward in time. And this becomes more and more clearer for angle displacement theta is equal to 45 degrees. So as you can see, with time the pendulum is sort of going out of phase from some kind of a simple harmonic motion. So let me bring this particular graph to my notepad. So this is quite interesting. You see, if we make a comparison between the solution of the simple pendulum for small angle approximations with that of the solution of the equation without small angle approximation, we come up with something really interesting, because the red line here is, of course, as I told you, is the SHM motion, which is a sinusoidal motion, and the blue line here represents the actual motion of the pendulum, right? Now, as I showed you earlier, for smaller angles, theta is equal to 15 degrees, 30 degrees, both of them were very, very close to each other. But for large angle, like 45 degrees, both of them sort of keep going out of phase with time. So as time is going forward, as the pendulum is moving, oscillating on and on in time, the pendulum develops a certain phase difference from the SHM. It is no longer an SHM. So now you may remember that if you have performed this kind of an experiment in a lab, maybe your teacher told you that please make sure that you only take small angular displacements when trying to create oscillations. Well, this is the reason. The reason is that the pendulum stops behaving as a harmonic oscillator for larger angles. So for considerably larger angles, the pendulum is not behaving as a harmonic oscillator anymore. The pendulum's motion can be approximated to be the same as a harmonic oscillator only for smaller angles, like 10 degrees, 15 degrees, 5 degrees, less than that. So for smaller angles, the solution of the nature of motion is that of an SHM. It behaves as a harmonic oscillator. It creates sinusoidal motion. But for larger angles, the pendulum's amplitude lags behind a sinusoidal function. So as you can see, the motion of a pendulum is not that simple. I mean, it is simple. It looks simple for small angles, but for larger angles, it is a little bit tricky. Yeah. Okay, so let us move ahead to the next topic that I wanted to discuss, which is the phase space trajectory. What is the nature of the phase space trajectory for a simple pendulum? By phase space trajectory, you may already know that when we talk about phase, we are basically talking about momentum. So if you look at what is the nature of the momentum and how it varies with displacement. Now again, I'm going to look at, or I'm going to do the analysis from two perspectives. One, I'm going to look at the solution that I have obtained for small angle oscillations, and from there I'm going to try to find out what is the relation between momentum and angular displacement. But I'm also going to do the solutions using the simulation that I've created, the program that I've created, where I'll obtain the momentum from the solution of the differential equation done by the numerical method, and then I'm going to compare both. So in a way, we will obtain the phase space trajectory for small angles as well as for larger angles. So let us do that also. So here the displacement is clearly theta, and the momentum is the momentum associated with theta, which is the angular momentum. I'll write it as p theta. All right. So how is p theta related to theta? Well, we can figure it out by looking at the solution that we have already obtained, which is theta is equal to theta naught cos omega t. So from there we can obtain what is the momentum. Now you may already know the definition for angular momentum, which is nothing but r cross p, where r is the radial distance from some kind of an origin O, and P is the linear momentum. So if we look at the pendulum, the original pendulum construction that we made, the P, that is the linear motion, is along the transverse direction, while R is along the wire, which is along the radial direction. Both the transverse and the radial directions are perpendicular to each other. So therefore, the cross product simply, it looks like R is replaced by L, and P is nothing but the definition of momentum, which is mass times velocity. L m L omega. So this is equal to m L square omega. So this is the angular momentum magnitude of a pendulum for SHM. When I say for SHM, I simply mean that for small angle approximations, what is the relationship that exists between angular momentum magnitude and theta? P theta is simply equal to m L square omega. What is omega here? Omega is nothing but the angular velocity, that is theta dot. And what is theta dot? Theta dot is equal to omega theta naught minus sine omega t, right? So theta dot is nothing but m L square minus omega theta naught sine omega t. So this is simply equal to minus m L square theta naught omega into root over 1 minus cos square omega t. If I take a square on both sides, this simply becomes p theta square is equal to m L square theta naught omega square 1 minus cos square omega t. However, what is cos omega t? I can obtain that cos omega t from here simply is nothing but cos omega t is equal to theta upon theta naught. If I use this to substitute in this equation here, it simply becomes p theta square is equal to ml square theta naught omega whole square 1 minus theta upon theta naught square. This I can further simplify by writing p theta square is equal to ml square omega whole square. If I take theta naught square inside, this becomes theta naught square minus theta square. Now what is m, l and omega? They are all constants of motion for this particular situation. So I can simply write this as some kind of a constant c, theta naught square minus theta square. So theta naught is the maximum amplitude, while theta is the angular displacement at any given point in time. So this can be further simplified to write as p theta square upon c plus theta square is equal to theta naught square. So what is the nature of this expression or equation? P theta square upon, let's suppose, some constant c, which can be written as some other constant, let's suppose a square plus theta square upon 1 square, or 1 I can just write it here as b square. So this is equal to, let's suppose, theta naught square. This is simply the equation that corresponds to an ellipse. Okay, this is an equation of an ellipse. Now it doesn't matter what a, b and theta naught are here in this situation, because I'm just trying to look at the nature of the trajectory in phase space. So if you plot the momentum with respect to the angular displacement, then you should get some kind of a elliptical trajectory. So let us try to do that. So here I have a program again in Scilab where I'm trying to plot what is p theta with respect to theta for some angle 10 degrees. Okay, so 10 degrees is small enough because I have done the analysis for small angle approximations. I have used that solution. So for that, if I come up with the graph, so this is the graph. So this is clearly a elliptical trajectory, right? So the y-axis represents the angular momentum magnitude and the x-axis represents the angular displacement. So clearly you can see that this is some kind of a ellipse that has been formed. So this is a phase space trajectory for small angles. Now the question is, what if we look at the phase space trajectory for larger angles, right? Now for that, again, I'll have to take help of some kind of a computation software, which I'm taking here, where I solve the equation of motion using some kind of a numerical solution for second order differential equations. And from there, I obtain the momentum. And from there, I plot the momentum with respect to increasing theta. So here what I'm going to do is I'm going to take the starting angle as 1 and the last angle as 179 degrees, and I'm going to look at 10 different plots of increasing theta. So let us run the program and see what we get. Whoa. Okay, so this is an interesting diagram here. So if I zoom in, this is the phase space trajectory for theta is equal to 1 degrees, which is clearly an ellipse, right? This is for a greater angle, again an ellipse, right? This is for a greater angle, again an ellipse. So for smaller angles, the phase space trajectory between the momentum in the y-axis and angular displacement in the x-axis looks like an ellipse. But when angle becomes larger and larger, clearly, as you can see, the graph sort of keeps on changing a little bit. The ends sort of taper a little, and this becomes like some kind of a eye. All right. So the inner circles I've obtained using small angle approximation. The outer circles I've obtained from the solution of the differential equation for larger angles. So this is the phase space trajectory for a pendulum starting from 1 degree of initial displacement to 179 degrees of initial displacement. So it is quite interesting to see, isn't it? It looks like some kind of a human eye or something. It is quite interesting. Yeah. So again, I'm going to do the analysis for both small angles as well as larger angles. Now, if you went through my video where I was discussing the Lagrangian, I have already calculated what is the kinetic and the potential energy. The kinetic energy here that I've obtained is simply written in terms of polar coordinates in this particular manner, while the potential energy is written in terms of the ground. Ground here is the lowest point of the pendulum. This is mgl1 minus cos theta. So the kinetic energy expression was this, but I already told you that since the length of the pendulum does not change with time, r dot is obviously 0. So the kinetic energy T is nothing but half m, r is nothing but the length L square theta dot square, while the potential energy V is equal to mgl1 minus cos theta. I want to look at how the potential energy varies for small angles as opposed to larger angles. So that approximation I want to apply here also. So if I apply the small angle approximation, I can approximate cos theta. Okay, so cos theta can be approximated for very, very small angles as 1 minus theta square upon 2. If I substitute that in the potential, this simply becomes mgl 1 minus 1 plus theta square upon 2, which is nothing but mgl theta square upon 2. So this can be written in the form of half ml square into g upon L theta square. So this is equal to V is equal to half ml square. Remember, it was the moment of inertia of the pendulum. G upon L is omega square and theta square. So clearly half I omega square is dependent on the setup, and theta is the angular displacement. So V is directly proportional to theta square. This, by looking at this, you can say that the nature of the potential energy should be a parabola. Okay, now what does the parabola signify? The parabola simply signifies that it's a harmonic oscillator. For small angles, as I have already mentioned before, the simple pendulum behaves like a harmonic oscillator. Therefore, the potential energy looks like a parabola, right? And the kinetic energy is simply given by this particular expression, which is half mv square. The sum of the kinetic and the potential energy is simply nothing but the total energy, which is E is equal to T plus V. So what I'm going to do is I'm going to look at how potential energy and the kinetic energy varies, and the total energy should remain a constant for both small angles as well as larger angles. Okay, so this is a program here. Let us run it and see what results we get. Okay, so the left hand side is for smaller angles, the right hand side is for larger angles. So as you can see in the left hand side, the blue graph represents the potential energy, which represents the parabola corresponding to a harmonic oscillator. The red one represents the kinetic energy. Now, of course, as potential energy decreases, kinetic energy increases, and as kinetic energy decreases, potential energy increases. And the black line here at the top is a straight line because the sum of potential and the kinetic energy is constant. That's just the conservation of energy principle. However, if you look at the right hand side, this is for larger angles from 1 to 179. Here you can see that this is not exactly a parabola, but for smaller angles, even this will approximate to a parabola. So for smaller angles, the potential energy will approximate to a parabola corresponding to a harmonic oscillator, but it is not necessarily true for larger angles. So there it is. For larger angles, the pendulum does not behave like a harmonic oscillator, and therefore the energy does not represent the potential energy does not represent a parabolic curve. But for smaller angles, it behaves like a harmonic oscillator. Therefore, the potential energy behaves like a parabolic curve. And the same with the nature of the motion. The pendulum executes simple harmonic motion for smaller angles, but it does not execute simple harmonic motion for larger angles. With time, the actual motion of the pendulum for larger angles lags behind some kind of a sinusoidal curve. So that is all the discussion I have for you today in terms of the simple pendulum. I hope you enjoyed the video, you learned something from it. So let me revise what we have done today. First, we obtained the equation of motion using the Newtonian approach in polar coordinates. Second, we obtained the same equation of motion but in terms of torque. Third, we obtained the same equation of motion in terms of the Lagrangian approach. And then we looked at what happens to the equation of motion. So we used the small angle approximations where we reduced sine theta to theta, and then we solved the differential equation to obtain the nature of the solution for a certain given initial conditions, where theta at time t is equal to 0 is theta naught, and theta dot, which is the velocity at time t is equal to 0 is 0. The solution is theta is equal to theta naught cos omega t. From here we can see that for small angle approximations, the simple pendulum behaves in a simple harmonic fashion. From here we can calculate the angular frequency, we can calculate the time period. It is interesting to see that the time period is independent of the mass as well as the angular displacement initially. I also obtained the similar kind of a graph from solving the differential equations for larger angles using some kind of a computation software, where we can see that for larger angles, the actual motion of the pendulum develops a phase difference. It lags behind an actual SHM with increasing time. We also looked at the phase space trajectory, where the nature of the momentum, how it varies with the angular displacement. We saw that it looked like an ellipse for smaller angles, but for larger angles it deviated from the shape of an ellipse. From the energy analysis, we can see that the potential energy is a parabola for small angles, but not so for larger angles. So that is all for today. I hope you learned something from this video. I'll see you in the next one. Thank you very much.